Hi, welcome to our webinar on Huawei's OptiX 800G and what it means to your DCI network. It's a pleasure to have you all here, and today we will learn about what makes our 800G work and how it can benefit your data center interconnect in your networks. When we look at the transformation of cloud architectures over time, what we see here is from a centralized cloud, singular locations, a trend towards more geographically diverse cloud builds. And there's several reasons. On one hand, it's for catastrophic failure prevention in case of an earthquake. These cloud locations need to be separated by a certain amount of kilometers. The second reason could be that in very dense cities, it's just hard to find enough space in one location. So therefore, you are forced to distribute the cloud over several locations in a city. And going forward, we see that the actual requirements from the users will drive a more geographically diverse cloud build-out, more distributed clouds. For example, we talk about video consumptions by end users. We need a lot of caching, and this caching needs to be, of course, where the user is. Or in case of gaming, low latency is a critical feature. So naturally, with this kind of feature requirements, the cloud itself, at least part of the cloud, will move closer to the user. And what we're going to see is sort of one building with a lot of servers inside, a wider distribution, acting as one logical data center. And it is interconnected using optics. And in this case, using coherent optics, which we are here about to present. So we will look at the traffic increase in DCI and data center interconnects. We see across all the domains, classical telecommunications, or all these vertical businesses, a very strong growth. And from a time range of 2019 to 23, the average network growth rate for DCI is around 45%. This means that your network capacity needs to double every 2 years. And there's a very strong pressure on reducing the costs in the network and also on physically enabling this sheer amount of capacity. In the old days, fiber may have been in abundance, but with new users coming in and building their own data centers, and also having to lease fiber resources, it becomes clear that we need to utilize the fiber to the fullest and put as much data on a single fiber as we can, because leasing fiber is a high cost. Also, what we see is for coherent optical port shipments for DWDM, the last year was an interesting year because there was this year where 200G took over the crown from 100 gig for DWDM coherent optics. At the same time, we also saw growth from 400G, 600G, and 800G line rates. And going forward, we expect also the diverse deployments depending also on the exact domain. Are we talking about metro DCI? Are we talking about metro regional, ultra long haul? These modems might vary, but certainly we see that 800G is becoming one of the dominant modem types in the future. And also the flexibility of 800G, where you can also dial down the rates in order to increase the reach even further, will make it a very interesting alternative to established modems, DWDM. So how do we use 800G? Which platform for DCI? And what are the important ingredients to make 800G work as a technology? So this is what we will discuss in this webinar in the following slides. So Huawei's OptiX Trans DC908 is our latest release for data center interconnect. And you see here, it was put a lot of effort into increasing the density of the solution, integrating line cards, make it even denser to save space. At the same time, these denser cards offer more functionality. We have 800G per lambda as our next step in per laser capacity. But at the same time, it's not just about increasing the rate per modem, because it doesn't necessarily mean that we double up the spectrum efficiency. We also need to increase the total amplified spectrum in the fiber. And in this case, we can provide up to 88 terabits per second per fiber, which is really a future-proof invest for any Metro DCI deployments. And moreover, in order to use this platform, it needs to be simpler and more intuitive and intelligent. And we have implemented many features which actually help the users with this. We have the 8-minute auto commissioning of the platform, and you will see later in the demonstration how easy it actually is to operate a device using the web GUI. At the same time, in our second release, we invested in several features which make it easier to monitor and operate the system, including the fiber plant. We have an advanced fiber health prediction, where we can see where the failures are about to happen, and we can actually, or the user can go out in the field and prevent potential fiber degradations from causing any outage. Another very interesting feature is a co-bundling fiber detection. It's especially important in areas where there's a lot of fiber deployed in the city, but maybe the exact locations are not known anymore, and the user would like to deploy a 1+1 optical protection. In this case, we have two fibers being used, one for the protection path, one for the working path, and of course they need to be geographically distinct. But in case it is not the case, in case there's really a span where these fibers go to the same duct, same cable, due to the lack of just knowledge about the fiber plant, we have monitoring tools which can detect that, meaning give the operator the absolute certainty that optical protection will work and not lead to an outage. And also we see that this platform, it's really not just about one, let's say, certain feature or a modem. It's really the platform. It's definitely a winning device. We won several awards at the Interop Tokyo or Light of Innovation Review. At the same time, this platform was analyzed by leading analysts, in this case by Global Data, and which deemed it to be a leader in several aspects. One is network management, and already what I mentioned, it's very easy to operate and use. And you will see later how easy it is. The other aspect is architecture, performance, and modularity. So you see in the right picture here, it's a compact 2 rack units high pizza box, which can host a variety of cards. It's either the transmission cards, where you can connect your client services and have a line-side optics going on fiber, or you have integrated modules for muxing and demultiplexing, or the amplification of these signals, all in one device. The client port capacity is up to speed, so we offer all the latest services and all the varieties, and you'll see later also very important mixtures. So you have a line card which can work as a mux sponder, and not just purpose built for, let's say, the most advanced node. The line interfaces are leading. We have a 2x800 gig line card, which offers in itself 1.6T line set capacity, and you can deploy 4 of these cards in this platform. And overall, the transport features, which includes also the line system here, are worth to mention. And overall, this makes it really a very sound, overall high-performance module and system. So let's look a bit deeper at what makes 800G work. So when we increase the line rates from 400G to 800G, we face, as researchers, as engineers, many new issues actually. On one end, it's noise. I mean, noise was always there, always will be there, but depending on the actual use case, it could be different. In this case, if we intend to use a slightly higher order modulation format, meaning we have more constellation points in our light set modulation, like you see here, like you just try to squeeze in more of these constellation points. Of course, they're more affected by noise, and this noise can not just come from optical amplification, it also comes from quantization effects in the D to A to D converters, and these quantization effects, they behave differently if we go to higher symbol rates. So we need to put in more intelligence to deal with actual quantization, which could be in the simplest step looked at as just a very simple effect. Laser phase noise also becomes more critical. If we go to higher order modulation formats, tiny changes of the phase can lead to higher bit error rates. So therefore, also need to invest not just in the actual algorithms, which can be improved, but also in the components to make sure that the laser phase noise from the lasers is contained to enable the next step of transmission. And nonlinearities in the fiber become more and more important, especially if we go to high order modulation formats. Just because even for the short reach, and depending on number of channels, single span transmission, and the channel power per laser, we can already easily observe nonlinear effects in the fiber. And they need to be dealt with. They need to be, or the modem needs to be designed in a way that these effects do not become limiting. At the same time, we have distortion effects which become more severe at higher symbol rates, higher baud rates. One very nice example is the dispersion. Chromatic dispersion, if we increase the symbol rate, meaning the rate by factor of 2, actually the detrimental effect of dispersion quadruples, meaning that the filter needs to become 4 times more, let's say, complex in its simplest implementation if we just double up the rate and keep the link the same. So it's still the same link, it's still the same system, but the filters become more complex. So we need more intelligence to make sure we design these filters in a way that power consumption is managed. So overall, we see that it's not just the algorithm which needs to be designed for the next rate, it's also the components which need to enable a larger bandwidth and better fidelity, higher fidelity, and it's also the line system. As we see here, the line system is a key to make sure that we can utilize the fiber more efficiently down the road. Day one, we can start with already the advanced Super C band transmission, or we can have 120 channels in the 50 gigahertz spacing. And then when traffic picks up, network demand picks up, we can seamlessly extend the system to C plus L band for a total of 11 terahertz amplified window. So this functionality combined with advances in low-power silicon photonics, where we miniaturize the modulators and receivers needed to bring the signals on the fiber, and also advanced signal processing, which is needed to combat more advanced detrimental effects. All of this is needed to really get to the next step and have an end-to-end optimized, holistically designed system. So one of the important features of Huawei's 800G, and here actually you see how this module looks like. It's a kind of cold pluggable module on a sled in this DCI platform. Here actually is a screenshot of the actual constellation, how it looks like. You see we really have more denser constellation points using 800G. One of the beauty features of this platform is it fits into 100 gigahertz spacing, which means it's really easier to manage. You know, numbers all are familiar to operators from the legacy 100 gigahertz grids. We can use off-the-shelf normal muxes, demuxes, which are designed for 100 gigahertz. And of course, we can utilize the fiber more efficiently. We can bring up to 88 terabits per second on a single fiber if we use C and L band. And at the same time, we have advanced and improved transmission distance. For example, for of course, the distance depends on fiber parameters, span loss, number of spans, amplifier types, number of neighbor channels, a lot of parameters. So you cannot just say this rate goes this distance. But for typical scenarios, the 800G is certainly the major application would be Metro DCI, although we have shown with China Mobile that this 800G is capable of more than 1,000 kilometer transmissions. Here was an article published on this in the Fiber Systems. And at the same time, the line rate can be dialed down to 400 gig, and we get ourselves really a long-haul transmission in really covering backbone networks, which is better than these small form factor 400ZR pluggables. And this is enabled, again, some key features here. As you already seen on this constellation, we use advanced constellation shaping, meaning the probabilities of each point are not equally distributed. So these bits are mapped on a constellation which looks a bit Gaussian in its way. And we use artificial intelligence to really design this constellation to match the channel optimally. So it's not just trying to optimize this for a simplified assumption of channel noise. We are optimizing these constellations to the actual channel, and every channel has different characteristics. That's the predicament using optical fibers. There's not one channel like the other. Once we go towards amplified transmission or even multi-span mesh networks. So therefore, we also need more advanced compensation schemes, can be pre-distortion or equalization for nonlinear effects, and of course, more advanced forward error correction. We're getting closer and closer to the channel limit, meaning there's not much room left to improve the FEC, but it still can be improved. At the same time, keep in mind that we need to make sure that the power consumption of the system is not getting too high, it's manageable. So advances on signal processing go hand in hand with a power optimal design. So in more detail, I think it's really a good idea to get a transparent understanding on what this actually line card does and what it looks like, right? So here we see this 800G line card, and when I say 800G, actually it offers a dual channel 800 gig. So here we have these 4 connections, so 2 times transmitter and receiver. So for a total line card capacity of 1.6 terabit on the line side. And on the client side, we can utilize here these ports really flexibly, either for 4 times 400G, or for 16 times 100 gig Ethernet, or for combinations of really flexible max bonding of 100 gig and 400 gig client rates. At the same time, our platform is not just a simple point-to-point Ethernet transport box. It's not your classic IP over DWDM, which lacks important transport functions, right? We have a regen mode, so you can use this platform really to regenerate your signal depending on the reach, depending on the network configuration, which you cannot do the same way with the same functionality using IP over DWDM. The same way, this platform offers all the functions which a classical full-blown OTN platform has, which are very critical to really having a simplified deployment, but at the same time protections against catastrophic failures. So the system offers optical line side protection. It offers intra-board 1+1 protection in case one board should fail. And it offers client 1+1 protection in case there's a failure on the client side. So all these are important features to really make the most of the platform, but at the same time to be prepared in case that there is a failure on a module or a fiber cut or a card outage. These things can happen eventually. So it's all about having the features in place which are easy to deploy and operate, but offer the protection. Because once there is a really significant outage in the system, there is no excuses. In this case, the CEO of one company calls the CEO of the other company. We have really a high escalation. So this needs to be prevented. And you need to have a system which really enables you to protect your network at various layers, various levels against outages. So we thought it's really best to show you hands-on what I hope this video can work. Let me just make sure I can start the video. Yes. So we recorded the demonstrations for you, what it actually looks like to put such a system in place. Here we see 2 of these pizza boxes, each one hosting a very simple baseline configuration to transmit 800G on the line side, to have client side traffic being monitored, to have multiplexer cards and amplifier cards. We see here the system is connected to a 100 gig E tester, and in between we have 80 kilometers of fiber, which is a typical scenario for data center interconnect, single span, 80 kilometers. We can simulate a traffic, and you see also the meaning of each of these boards, right? We have an LCD panel for monitoring of baseline functions. We have the amplifier board. This is the 800G line board, having 2 800 gig line services and a variety of clients. This is the MUX board, 100 gigahertz spacing, and the amplifier card, which is already a reserved L-band port for future upgrade. So this is what a system looks like, and how do we configure it and bring it up to speed is pretty simple. We log into the web GUI. We see the traffic being configured and running. There's should be no alarms. Yeah, we see there's no alarms. All connections are normal. System is functioning as intended. So this is how it's really straightforward and easy to use this web GUI to run the system. Again, all the client statuses are okay. Everything is green and working. We see here in the client tester, the system has been running for 21 minutes without failures. And now, just to see how what would happen, we disconnect the fiber from the amplifier to simulate a fault. Right away, we observe a failure in the system in our network management. We see a list of the critical minor failures. We obviously see that the client traffic is not working anymore. And after reconnection, everything is back up to normal. Alarms are cleared. The services are restored, and the client traffic monitoring shows us we are okay. So this is as simple as it can be. You know, two pizza boxes equipped with all necessary functions to get your DCI kickstarted. Yeah, that's DCI as simple as 1, 2, 3. Okay, so I already mentioned that for a sophisticated DCI platform, or for the Ethernet G to really unfold its true potential, you also need the line system. As I mentioned, we need more sophisticated lasers, which are tunable across wider ranges. In this case, the super C-band, while having a lower phase noise. We need super C-band WSSs, which are wavelength selective switches, offering for potentially mesh networks optical switching capabilities. And of course, we need the amplifiers, right? Which, you know, we developed new super C-band optical amplifiers, which have a wider gain range. We optimized the flattening, so the ripple of the amplification, and also the noise figure to make sure that these 120 channels in 50 gigahertz spacing are as seamless as your 80 channels in the classical C-band today. However, this is not enough. You know, if we operate C plus L bands, we realize that it's not the same as having like the C-band alone. And what's the reason for it? Well, if we look at the line system, we see actually that the C and L band require dedicated amplifiers. You know, with dedicated C-band EDFA and L-band EDFA. It's not just one component anymore. Same holds true for optical switches these days. They're dedicated ROADMs for C and L-band. And now what happens is, what if the C-band fails? You know, what if we have a fiber cut or an amplifier goes down in the C-band? You know, our plug-and-play operators would expect, well, C-band fails, but the L-band should be protected, right? There's no reason, logically speaking, why the L-band would be affected if we, you know, don't get deeper into the fiber design. But actually, there is a reason. You know, we see that the fiber has certain effects that actually make things more complicated. And in case there's an effect called stimulated Raman scattering, which is quite useful for deploying Raman amplification, we can have a shorter wavelength pump amplify wavelength at higher wavelength, longer wavelength. And this also happens in the system. So actually, our C-band transmission amplifies the L-band naturally, without, you know, us maybe even wanting it to happen. But in case the C-band disappears due to failure of the amplifier, for example, we have a huge drop in this pumping coming from the Raman effect. And actually, without any precautions, and there could be a very large drop in optical power of the L-band. It can be as high or even higher than 10 dB, depending on the link. And I think it's clear that for a 10 dB drop, we will have an outage in our system. The system will not work also for the L-band. So what needs to happen is we need to have the tools in place to prevent this from happening. And we developed a microsecond level detection algorithm to really monitor these transients and balance the L-band amplifiers in a way that we do not get the severe system outage in case there is a C-band failure. And we have only a very small drop using this transient monitoring to less than 1 dB, which is typically part of the system margin anyway. So there will be no disruption of the outbound traffic, which again goes into the way we need to build not just high bit rates. A high bit rate alone does not help you. It needs to be easy to operate and maintain. It needs to be safe against all kinds of outages. Only then you have a secure system, a stable system, which can unfold the potential of our 800G modems. So coming to the last slide, our 800G has been already in commercial use with several leading operators. And all of you on the call in the webinar, you are free to contact your local sales rep of Huawei to get your own demonstration of 800G to see how our 800 gig can benefit your network, how it can help you to drive down the costs of future network build-outs. At the same time, I'd like to emphasize that researchers don't stop here, right? We already look way beyond. This year we had a leading field trial demonstrating 1.6 terabit, or even higher than this, beyond 1.6 terabit transmission on a single wavelength, thus more than doubling the capacity of our product in this research experiment, proof of concept. But we demonstrated, various reaches, rates of even beyond 1.8 terabits. So we see innovation doesn't sleep, and already while you are testing and deploying and rolling out our 800G, already think ahead what will happen in 3 to 4 years from now to make sure that whenever demand really hits, we're ready to provide you our next generation solution to further increase the fiber throughput. So with this, I would like to thank you very much for your attention. We can end the presentation here. I also would welcome you, in case you didn't have so, to write your questions into the webinar, into the Q&A, and I can answer them. Also, please, after you leave, stay on the line. There will be a short survey in the window, just 3 very short questions, which I would like you to answer. Okay, I will just go to the questions here. Let me see. Could you provide the real modulation used? Is it 16 QAM? I've shown in one of the slides. It's probabilistically shaped 64 QAM. So this is the modulation of choice for 800G. It's a single carrier transmission, and it's 64 points. They're not transmitted with the same probability, which is the key of constellation shaping, and which is the technique which we developed here also at Huawei to become more advanced. Let me see more questions. Does the real-time DSP really include the AI-based nonlinearity compensation? So the 800G product in itself, in a chip, in the modem, does not include, an AI equalizer yet. What it includes is, there is, today we use artificial intelligence to configure settings of the modem, and these AI computations, they don't happen in the DSP chip itself. They can happen somewhere else in the system. But in the future, we also intend to, this is a research and innovation in progress as we speak. We also intend to pull in some of these AI functions into the actual modem. If we for certain the use cases, it actually brings a benefit. We have analyzed various blocks in the processing chain, and actually there can be a benefit, for example, for a nonlinear equalizer. So in the future, we intend also to bring this into the actual modem. Today, we use this AI intelligence to configure the modems. Can I please explain the graph I showed in the last slide? Yes, definitely. Let me just start the sharing again. It's always nice for me to explain something more technical. So this is the last slide. I assume the question was regarding this graph here. So what you see here, first of all, is that the modulation format for this beyond 1.6T is also going beyond the 64 QAM we currently use now for 800G. This is actually a probabilistically shaped 400 QAM, yeah, 400 QAM. And what we did here was, we varied the launch power per channel into the optical fiber. We see that the optimum power is somewhere around 6 to 7 dBm. And we observed the achievable information rate, which, if you speak to a researcher, means what could you do if your forward error correction was really ideal. Of course, we need to say in an actual product, we would not have an ideal forward error correction. There will be a little gap between this curve and a curve which one can implement in the modem. But for the sake of exploring the boundaries, researchers accepted this metric to analyze what is achievable. So what we see here, that with an ideal forward error correction, we can achieve an information rate between, say, for a 60-kilometer link at an 8 dBm input power per optical channel of more than 1.8 terabit per second per laser. So a single laser has a data rate of more than 1.8 terabits. So it's way beyond 1.6T. And we, in this field trial with a tier 1 operator, we have analyzed actually various different scenarios. This was just one of the scenarios. We also looked at different modulation types. We looked at shorter distances and higher order modulation. We looked at longer distances, more than 1,000 kilometers, and lower order modulation. And I think what we have shown is also that with our next generation modem, it's not just about the 1.6T and beyond, it's also about the 800 gig, which in this case would become a rate which can cover whole backbone networks, right? Because today, today's product is really focused and best used for metro DCI. So the 800G, although it can reach more than 1,000 kilometers, it's more probably this more ideal settings, and not every link can go this far. But for the next generation of these products, which we currently research and which can go beyond 1.6T, the 800G mode will be a true long-haul backbone 800G, which can really work for any link in the backbone network, regardless of the distance and the configuration. So I think this is one of the key takeaways which we had in this field trial, that the next gen of our products would offer the 800G mode, which is long-haul capable. And in the end, this is what we want, right? We don't want to have this 800G just for the short reaches, right? We need to evolve it and to improve it to really cover majority of networks out there. And with this, I would like to conclude this webinar. Thank you very much.